Tesla just closed Q3 2025 with record numbers. 447,450 vehicles produced and 497,099 delivered worldwide. That is only the beginning. In 2026, the arrival of the Tesla Model 2 is set to push these figures even higher, as this car is poised to mark the end of China's EV dominance by combining a truly affordable price with driver-focused technologies that feel anything but cheap. What is hiding inside this small car that makes it punch above its class? How does it deliver instant throttle response, strong hill climbs, and lower energy use at the same time? And why might legacy and new Chinese rivals struggle to copy it quickly? Stay with Motivation with JKK as we open the car up layer by layer and reveal the engineering that could flip the market. Subscribe and turn on the notification bell so you never miss our next deep dives. 1. What makes the Tesla Model 2 outperform Chinese EVs in real-world driving? Tesla Model 2 delivers a punchy throttle feel because its motor is engineered for high torque per kilowatt and low loss. And the pieces of that design work together rather than in isolation. The IPM rotor uses ferrite assistance and carefully shaped flux barriers to blend magnet torque with reluctance torque while guiding flux along short, efficient paths, which trims iron loss as speed rises. That rotor is paired with a stator built from very thin electrical steel laminations of about 0.27 millimeters coated for low loss. Since eddy current loss scales roughly with the square of lamination thickness, moving from 0.35 millimeters to 0.27 millimeters can cut that component by around 40% when other factors are constant. Completing the picture, direct ending cooling through oil jets or slot channels raises allowable current density without pushing temperatures beyond safe limits. A change that often delivers double-digit gains in continuous torque, typically 10 to 30% depending on architecture. With these elements aligned, Tesla Model 2 snaps to the throttle at low speed, holds strong mid-range pull without chasing a higher peak rating, and converts more battery energy into motion rather than heat at cruising speeds. That same system's thinking carries over to braking, where efficiency and feel reinforce one another. Brake-by-wire measures pedal force and asks the motor for as much regenerative torque as conditions allow, calling on friction brakes only for the remainder. In everyday decelerations, this means regeneration handles most of the work, commonly 70 to 90% in urban cycles. The arithmetic illustrates why it matters. A 1.66-ton car at 50 kilometers per hour carries 154 kilojoules of kinetic energy, or 0.043 quat-hours, recovering 70% returns about 0.043 quat-hours, 0.0303 quat-hours to the pack. In stop-and-go traffic, these small wins accumulate and appear as a clear drop in WH per kilometer. In case you find the numbers and math feel overwhelming, click the link on the screen to learn more about Tesla's regenerative braking. I've already covered it in quite a detailed breakdown. Because regeneration is doing the heavy lifting, the friction hardware can be smaller without compromising safety. Trimming 1 to 3 kilograms of rotating and unsprung mass at each corner reduces wheel inertia, lets the suspension follow the road more faithfully, and makes the steering feel cleaner. This directly complements the motor's high torque per kilowatt, since more of the effort shows up as real wheel speed change rather than overcoming excess inertia. When the propulsion and braking systems work in concert, the road result is consistent and easy to predict. Tesla Model 2 jumps from 0 to 50 km/h quickly, keeps pulling on climbs because iron losses are suppressed, and windings stay cool, and needs fewer kilowatts to make the same old torque in mixed driving. Each deceleration then returns a little more energy to the battery, lowering W-hours per kilometer and extending range by a few percent in normal use, and even more in city traffic. The option to meet range targets with a smaller pack further reduces mass, while preserving the lively feel. Heat loads in the motor and brakes stay lower, so acceleration and stopping remains stable through repeated cycles. Pad and rotor, where slows and pedal feel stays natural thanks to smooth blending. Low torque ripple from the thin laminations and optimized electromagnetics keeps the front end precise during lane changes or merges, which is exactly the kind of confidence drivers notice from behind the wheel. Which part of the Tesla Model 2 impresses you most? A. Snappy throttle and quick launches. B. Regenerative braking that lowers hours per kilometer and extends range. C. Lighter brakes that make steering and body response smoother. Cast your choice A, B, or C. 2. What makes the Tesla Model 2 go farther, weigh less, drive more smoothly, and have a lower total cost of ownership than Chinese EVs? Tesla Model 2 uses a silicon carbide inverter instead of an IGBT design. Silicon carbide supports higher switching frequency, tight power module integration with a very short DC bus that lowers equivalent inductance and resistance, and precise field-oriented control with accurate dead time compensation. Together, these choices let Model 2 travel farther, weigh less, feel smoother, and deliver a lower total cost of ownership than many Chinese EVs that still rely on IGBT hardware. Why does the Model 2 go farther? Higher switching frequency makes the phase currents closer to scan waves, so current ripple falls and both iron and copper losses in the motor drop. Silicon carbide devices also incur much lower switching loss at the same voltage, so the inverter burns less power as heat. Real-world gains of roughly 1.5 to 3.5 percentage points in inverter efficiency are common. And overall drivetrain efficiency often rises a few more points thanks to cleaner currents and accurate FOC. In urban cycles where the car spends most of its time at partial load, this improvement shows up as a 3 to 8% reduction in WH per kilometer, depending on conditions. With the same battery size, Tesla Model 2 delivers more hours to the wheels and covers more distance, or it can hit the same range with a smaller pack. Why is the Model 2 lighter? Lower loss means less heat to reject, which allows smaller heat sinks, radiators, and pumps. The ability to switch faster also enables smaller inductors and capacitors. When the power stage is packaged as compact half-bridge or full bridgeage modules with a short DC link, the inverter shrinks and can be mounted closer to the motor to shorten the DC path. For a small to mid-size car, these optimizations can remove roughly 4 to 10 kilograms from the drivetrain. Less mass improves energy use and gives the chassis a more agile baseline. Why does the Model 2 feel smoother? Lower phase current ripple produces smoother shaft torque.